Today, we're going to pull back the curtain on one of machine learning's most powerful and honestly brilliant tools, the support vector machine. Alright, so here's our game plan. We're going to follow a simple journey, starting with a really basic problem, and then see how the SVM cleverly evolves to tackle more and more complex challenges. It's a great story. So let's kick things off with this question right here. How does a machine choose the best line to separate the imagine you've got two groups of things. It seems simple, right? But figuring out the single best way to draw that line, well, that was a surprisingly tough nut to crack for a long time. So this is what we call the separation problem. And when you first look at it, it seems almost trivial. You've got two clear clusters of data. So the challenge isn't just drawing some line. The real problem is that there are just so many possible lines that look like they do the job. So how in the world do we choose? Is one of these lines actually fundamentally better than the others? This is the exact puzzle that support vector machines were born to solve. And this brings us to the core, brilliant idea behind the support vector machine. It uses this really powerful and, super intuitive analogy that just changed the game completely. Okay, first, a little bit of terminology. Instead of just calling it a line, we're going to use the more formal term hyperplane. And this is a great word because it doesn't matter if your data is in 2D, 3D, or 1,000 dimensions. Hyperplane always works. Now, here's the breakthrough idea. The goal isn't just to separate the groups. It's to find the hyperplane that creates the absolute widest possible street, or what we call a margin, between them. This wide street isn't just for looks, it represents a much more confident and robust boundary for our classification. And what about the data points that are sitting right on the edge of this street? Will those have a special name? Support vectors. You can kind of think of them as the pillars holding up a bridge. They're the toughest points to classify, and they're absolutely critical for defining where that boundary goes. And this leads to something really fascinating and super efficient about SVMs. See, unlike a lot of other models that get influenced by every single data point, an SVM's boundary is decided only by these few support vectors. You could literally move any of the other points around, and as long as they don't cross into that margin, the hyperplane won't even budge. Pretty cool, right? So how does the machine actually find this widest street? Well, it all boils down to a really beautiful math problem. Turns out the width of that margin is directly related to a value from the hyperplane's equation, which we're calling RW here. So to make the margin as wide as possible, the machine has a super clear goal. Just make that RW value as small as it can be. It's a really clean and elegant optimization. Okay, so this widest street idea is perfect for clean, perfectly separated data. But let's be real. The world is messy. Data is messy. The original method, which we now call a hard margin SVM, demands absolute perfection. No point can be on the wrong side. So what happens if you get an outlier, or if the data just isn't perfectly separable? Well, the model just breaks. It can't find a solution. To get around this, we came up with something called the soft margin SVM. Instead of demanding perfection, it just aims for the best possible fit. This makes the model way more flexible and robust, because it actually allows for a few mistakes. And how does it do this? Well, it uses something called slack variables. You can think of them like a budget for errors. Each little variable measures how much a data point is violating the margin, and the model's job is to keep that total error budget as low as possible. And this is where the parameter c comes in. It's basically a knob we can turn to control the penalty for those errors, so we can balance things out. Do we want a really wide general margin, even if it means a few more mistakes? Or do we want to get the classification right on our training data, even if it means a narrower street? C lets us make that trade-off. All right, let's move on to our next big challenge. And honestly, this is the most ingenious part of the whole SVM story. What happens if your data can't be separated by a straight line at all? Just imagine this. You've got one circle of data points completely surrounded by another circle of points. A straight line or a flat hyperplane. It's just not going to work. No way. The problem seems totally unsolvable in its current state. But the solution comes from this really brilliant mathematical observation. Way down in the guts of the SVM's calculations, the relationship between any two data points is measured using a simple little operation called the dot product. It's really just a number that captures how similar 2 points are. And this single dependency, well, that's the key to everything. This is where we get the famous kernel trick. It brilliantly swaps that simple dot product with a much more complex function, a kernel function. Now here's the wild part. This function doesn't actually move the data. It just calculates the dot product as if the data had been projected into some new higher dimension. It's like a mathematical portal to a whole new perspective. And this is the magic that happens. In this new, higher dimensional space, our hopelessly tangled data suddenly becomes perfectly separable. A simple, flat hyperplane can now just slice right through it. The absolute genius of this is that we never had to actually compute those new dimensions. The kernel function gave us a shortcut. We didn't change the algorithm at all, just its perspective on the problem. So when you put it all together, maximizing the margin, adding soft constraints to handle noise, and then using the kernel trick for nonlinearity, you get the support vector machine, an incredibly versatile and really powerful tool. And what this means is you can plug and play different kernel functions to create all sorts of decision boundary shapes. If you need a flexible curve, you might use a polynomial kernel. If you need to draw a really complex, localized boundary, the RBF kernel is perfect for that. It's this flexibility that makes the SVM such a workhorse for so many real-world problems. So, let's just recap the whole journey here. The SVM story starts with this simple, elegant idea. Find the widest possible street, a margin that's defined by only a few critical support vectors. Then, to handle messy, real-world data, we add soft margins to allow for some mistakes. And finally, to solve what seems like impossible non-linear problems, we use the mind-bending kernel trick to change our perspective. It's just a beautiful, logical evolution of a powerful idea. And that really leaves us with a final thought to chew on. If we can teach a machine to draw the perfect line, not just in 2 dimensions, but in any dimension, what other incredibly complex decisions can we train it to make? It just goes to show you that sometimes the most powerful ideas in artificial intelligence start with something as simple as trying to draw the best possible line.